Okay, we're continuing with Chapter 1 in the geometry textbook. In this video, we're going to go through section 1.7, which is on the formal proof of a theorem. So we've already looked at the idea of proofs. In 2 sections ago, we looked at the introduction to geometric proof. In the previous section, we also did a lot of work with proofs as well. And so, but now what we're doing is we're going to take a lot of the concepts that we've already learned and apply them to understand, formally exactly how a theorem is proved. We have a sense for how proofs work, but now we're going to really look formally at the proof of theorems, because remember, theorems are what you prove. You don't prove postulates, you prove theorems. As we learned at the beginning of the chapter, you make informal and formal definitions, and then combined with that, you have postulates, and then when you take all of that together, you can make theorems, which are like a natural consequence of the definitions and postulates. And it's the theorems that you need to prove. Theorems are not definitions. Theorems are a consequence of the definitions and you have in the postulates, the definitions you have made and the postulates you have stated. So you need to prove theorems. And so that we're going to now look at the formal way you prove a theorem. But now, as I've mentioned previously, this course isn't designed for mathematicians. This is more for non-math majors, engineering, business, biology, chemistry, for people just that are going to apply mathematics in their field. So we're not going to be going into that much detail on proofs. That's more for math majors. We're just going to focus on the geometry concepts. So that's why we're not going to work any example problems on related to proofs. The previous section had all the example problems were proof related. That's why we didn't work any example problems from 1.6. But we are going to go ahead and just read through these sections just to get a sense for what they're talking about. And one thing to note, though, is that you might ask yourself, so are all of these proof techniques, everything we're learning in this section about the formal proof of a theorem, is this general techniques for all of math, or is this just related to geometry? No. These are concepts that, what we're about to learn in this section, this is applied to all of math. This isn't just related to geometry at all. I mean, sometimes it is, but in general, this is the idea of proving theorems. All these proof techniques are applied in all of math. So it'll be interesting to read through it. All right, recall from section 1.3 that statements that can be proved are called theorems. That's right. A theorem was a statement. We talked about how a theorem was a statement that you could prove, which is different from like a postulate, for example. You don't prove a postulate. To understand the formal proof of a theorem, we begin by considering the terms hypothesis and conclusion. The hypothesis of a statement describes the given situation, whereas the conclusion describes what you need to establish. When a statement has the form, if H, then C, the hypothesis is H and the conclusion is C. Some theorems must be reworded to fit into the if-then form so that the hypothesis and conclusion are easy to recognize. All right, so let's look at an example. Give the hypothesis H and conclusion C for each of these statements. Okay, if 2 lines intersect, then the vertical angles formed are congruent. So they're saying the hypothesis is if 2 lines intersect, and the conclusion is then the vertical angles formed are congruent. So this is a little bit confusing to me, because when I think of the word hypothesis, I think of, the scientific method, the hypothesis. It's like a claim you're making. It's like your theory. But to me, like given, the given is not like you would do at the science fair, right? The hypothesis of your project, science project. To me, this feels a little bit different. Like, so if 2 lines intersect, that's a hypothesis. To me, that's more of a fact. It's not a hypothesis. I always thought about hypothesis in science as something you're trying to prove. You're trying to prove the hypothesis, right? Well, we're not trying to prove if 2 lines intersect. That's a fact. We're stating that as that's a fact of the situation. Then the vertical angles formed are congruent. So they're calling that the conclusion. So when it comes to these math proofs, it seems as though the hypothesis, it takes on a little bit different of a perspective than you would think about it from the standpoint of a science fair, scientific method the word seems to be being used a little bit differently here. Okay, all right angles are congruent. So here you can try and put this into an if-then form, but the hypothesis is if you have a right angle, and the conclusion is then that means that, well, okay, no, the hypothesis is if you have two right angles or more than one right angle, then the conclusion is that they're congruent. So let's see. If two angles are right angles, then these angles are congruent. Yeah, so that's the if-then form. If two angles are right angles, or you have multiple right angles, then those angles, the conclusion is those angles are congruent. Yeah. Okay. Parallel lines do not intersect. So if you have two or more parallel lines, then they're not going to, well, I guess you would probably say that if you have two lines that are parallel, then they won't intersect. That's the hypothesis is you have two lines that are parallel. If two lines are parallel, then these lines do not intersect. And the conclusion is the lines do not intersect. Okay. Lines are perpendicular when they meet to form congruent adjacent angles. This one's a little bit tricky. So, because the if is like put second here. So, if two lines meet to form congruent adjacent angles, then the lines are perpendicular. You see the hypothesis? The hypothesis is on the right this time. It's mentioned second. So, hypothesis, two lines meet to form congruent adjacent angles, then the two lines are perpendicular. All right. Why do we need to distinguish between the hypothesis and the conclusion? For a theorem, the hypothesis determines the given and the drawing. The given provides a description of the drawing's known characteristics. The conclusion determines the relationship that you wish to establish in the drawing. Yeah, it's just like a labeling for the whole structure of the proof. The written parts of a formal proof. The 5 necessary parts of a formal proof are listed in the following box in the order in which they should be developed. Okay, so the essential parts of the formal proof of a theorem: statement states the theorem to be proved. Drawing represents the hypothesis of the theorem. Given describes the drawing according to the information found in the hypothesis of the theorem. Proof describes the drawing according to the claim made in the conclusion of the theorem. Proof orders a list of claims, statements, and justifications, reasons, beginning with the given and ending with the proof. There must be a logical flow in this proof. So, yeah, the statement is telling you what the theorem is about. You know, what the theorem is. The drawing is like in coordination with the given. It's making the given very clear. This is the facts you're starting with, which is like the hypothesis, right? Then you have the proof, which is like, you go through all the proofs, the proof steps to get to the final proof, which is it describes the drawing in relation to the claim that you're making for the theorem, the conclusion of the theorem. The proof, the given and the drawing sum up the hypothesis, and the proof sums up the conclusion of the theorem. All right. The most difficult aspect of a formal proof is the thinking process that must take place between parts 4 and 5. Right, of course, the whole proof. This game plan or analysis involves deducing and ordering conclusions based on the given situation. One must be somewhat like a lawyer, selecting the claims that help prove the case while discarding those that are superfluous. In the process of ordering the statements, it may be beneficial to think in reverse order, like so. The proof statement would be true if what else were true? Yeah, you could go in reverse. That's another method you could use. You could think about. You could start with you kind of like assume that the proof is true, the conclusion is true, and see if you can go backwards to get to the given. But yeah, obviously the hard part about proving a theorem is the proof itself, what it's all about. The final proof must be arranged in an order that allows one to reason from an earlier statement to a later claim by using deduction, perhaps several times. Yeah, it's like a making a convincing argument, but it's deductive though. You provide these formal statements that prove that officially, establish a truth of the statement. Where principle P has the form if H then C, the logical order follows. So the hypothesis, statement of the proof, the principle, and conclusion. So let's keep going. Let's take a look at these examples. Consider the following theorem, which was proved in example 1 of section 1.6. If two lines are perpendicular, then they meet to form right angles. Okay, so let's prove that we're going to write the parts of the formal proof of this theorem. So, okay, there were 5 parts, essential parts of the formal proof of a theorem. So you first state the theorem. If two lines are perpendicular, then they meet to form right angles. Okay, now the hypothesis is that two lines are perpendicular. And so in these next 2 parts, it's a combination of the hypothesis and the drawing and the given. So make a drawing to fit the description of what perpendicular means. Remember, the basic definition of perpendicular doesn't mention a right angle. It's just that 2 lines intersect to form congruent adjacent angles. Okay, that's what perpendicular means. So let's see. There's the drawing. But we're not going to put this, because that's not technically what perpendicular states, anything about a right angle. Okay, so you write the given statement, given line AB is perpendicular to line CD, intersecting at E. Now then you write the prove statement. What are you trying to prove? That they form right angles. The adjacent angles are right angles. So they meet to form right angles. That's the conclusion. So we want to prove that angle AEC is a right angle. And then, but you could continue that further if you wanted to prove that the rest of the angles are also right angles. And then you construct the proof, the actual proof going from the given to the prove statement. And in the previous section, we actually did the proof. All right, the converse of a statement. The converse of the statement, if P then Q, is if Q then P. That is, the converse of a given statement interchanges its hypothesis and conclusion. Consider the following. If a person lives in London, then that person lives in England. If a person lives in England, then that person lives in London. So yeah, this is associated with the reversibility of the statement. When you reverse if you have a conditional statement and you reverse it, that's called the converse. As shown above, the given statement is true, whereas its converse is false. Sometimes the converse of a true statement is also true. In fact, example 3 presents the formal proof of Theorem 1.7.1, which is the converse of Theorem 1.6.1. Okay, so yeah, sometimes the converse of a conditional statement is true and sometimes it's not. But what you can do is you can think about that we can prove a theorem and then also prove the converse of a theorem. We'll have to prove that it is reversible or that its converse is true. Once a theorem has been proved, it may be cited thereafter as a reason in future proofs. Thus, any theorem found in this section can be used for justification in proof problems found in later sections. So yeah, once you prove a theorem, then you can then use it as a reason to prove other theorems. The proof that follows is nearly complete. It is difficult to provide a complete formal proof that explains the how-to and simultaneously presents the final polished form. Example 3 illustrates the polished proof. You do not see the thought process and the scratch paper needed to piece this puzzle together. Okay, yeah, so what they're saying here is that the ideal proof is going to contain all of the information about the how-to, but also being polished and cleaned up. You know, you don't want to, when you're actually building the proof, you might have all kind of scratch paper and all this information all over the place, but you're not going to present it that way, right? But you don't want to clean it up too much to where it doesn't present the full how-to of the proof. So it's kind of a balance. Perfect. You want to find the perfect balance. All right, warning, you should not make a drawing that embeds qualities beyond those described in the hypothesis, nor should your drawing indicate fewer qualities than the hypothesis prescribes. Yes, we talked about this before. You want to read what's given, read the hypothesis, and it's like with perpendicularity. You might be tempted to say, okay, if you said 2 lines are perpendicular was the given, oh, well, then you want to put that they're right angles. Well, no, the definition of perpendicular doesn't say anything about right angles. So you want to include only exactly what's given based on the pure definition or definitions of what's given. Okay, the proof of a theorem is not unique. For instance, students' drawings need not match even though the same relationships should be indicated. Certainly, different letters are likely to be chosen for the drawing that illustrates the hypothesis. So yeah, people you can find subtle differences if 2 people separately prove the same theorem. You could absolutely see subtle differences in the drawings, etc. Maybe even the reasons. Once you get to more high-level proofs, and there's a big array of theorems that you could potentially use, and then maybe even the path to get to the proof is going to be slightly different. All right, theorem 1.7.1, if two lines meet to form a right angle, then the lines are perpendicular. So that's the converse of the previous theorem that was proved, that if two lines are perpendicular, then they meet to form a right angle. So the hypothesis here is that two lines meet to form a right angle. So we can make, there's the given, and that line A, B, and CD intersect at E, so that angle AEC is a right angle. So these two lines meet to form a right angle. They're not perpendicular. They just meet to form a right angle. That's it. And so to do the proof, you can think about, well, we know this is a straight angle, AB. So since this is a right angle, that means this is going to have to be a right angle. Okay, we've got a vertical angle here. Vertical angles are congruent. I think we proved that already. Here's another vertical angle. So all of these are right angles. And so there you go. All the adjacent angles are congruent. That means the lines are perpendicular. So, another way we could have done it, like, there's different paths you can take. So we know that since this is a straight angle, AB, and this is a right angle, then that must be a right angle. But we know this has to sum to 360, going all the way around the point. So this is, well, also this is a straight angle as well. But maybe there's no way to prove that since you have a straight line going through here, that means that these two also must be congruent. I guess that's not really, we haven't made a statement about that. I was thinking that, since this line is a straight line going all the way through, and it's not changing directions, well, that means that these two angles have to be congruent as well, but we never formally proved anything like that. So we'd have to go to the fact that, look, we've got vertical angles here, congruent to this, congruent to this. So all of the adjacent angles are congruent at the intersection, so the lines are perpendicular. And that's what they, I just proved that informally, but that's what they go through more officially here. Let's see, let me make sure that's exactly how they did it. So they intersect, AC is a right angle, 9 degrees, straight angle. So the CEB is also a right angle. Yeah, see, CEB is a right angle. And then I think they use vertical angles next. Oh, well, no, that's all they need. You just showed that the two angles, that you have the intersection and the two adjacent angles are congruent, and that's all you need to show perpendicularity. Two lines form adjacent angles. I guess because, even this is technically all you need. That the two lines intersect, and do they form adjacent angles? Are these two adjacent angles, do they form congruent adjacent angles? If that's the case, then they're perpendicular. And that's what they proved, that angle AEC is congruent to angle CEB. But then why exactly, if the line extends through the point, if the line extends through the intersection point, are the other angles also congruent adjacent angles on the other side and also right angles? You would just use the fact that you have two vertical angles on the other side. There's a vertical angle pair here, vertical angle pair here. Several additional theorems are now stated, the proofs of which are left as exercises. This list contains theorems that are quite useful when cited as reasons in later proofs. A formal proof is provided only for theorem 1.7.6. So here's some more theorems. And again, you can use these in future proofs. If two angles are complementary to the same angle or to congruent angles, then these angles are congruent. Interesting. So if two angles, so if you have angle A and angle B are complementary to the same angle, so if you have angle C, so that means angle A plus angle C is, well, the measure of angle A plus the measure of angle C is equal to 90, and the measure of angle B plus the measure of angle C is equal to 90, then those angles are congruent because, you could just do some algebra here. Angle A is equal to 90 minus measure of angle C, and angle B is equal to 90 minus measure of angle C, so they're both equal. And then it says, or to congruent angles, if they're both complementary to the same angle, or to congruent angles. So if angle A is complementary to angle C and angle B is complementary to angle D, then angle A is complementary to angle B. So, yeah, I just informally proved it, right? But that's not an official proof. Okay, if two angles are supplementary to the same angle or to congruent angles, then the angles are congruent. Yeah, same thing. Any two right angles are congruent, of course. That seems kind of redundant, a redundant statement, but okay. If the exterior sides of two adjacent angles form perpendicular rays, then those angles are complementary. What exactly are they saying there? But they go into detail here. Let's take a look. For theorem 1.7.5, we create an informal proof called a picture proof. Although such a proof is less detailed, the impact of the explanation is the same. This is the first of several picture proofs found in this textbook. In figure 1.67, the square is used to indicate that ray BA is perpendicular to ray BC. So, okay, let's see. Oh, okay, the exterior sides of two adjacent acute angles. Okay, that's what I was missing. You've got the exterior, here's two adjacent acute angles 1 and 2, and their exterior sides are perpendicular. Then those two angles are complementary. I mean, that's obvious, right? But to do a formal proof, it's, to do a formal math proof, it's you have to be rigorous. But I mean, you could see if you draw the correct picture here of what's given, then obviously the measure of angle 1 plus the measure of angle 2 is going to be 90 degrees. That means they're complementary. And I'm sure that they'll do you could make another theorem that says if the exterior sides of two adjacent, well, you wouldn't say acute, but angles form a straight angle, or two rays that are in opposite directions, then those angles are supplementary. You kind of do an extension of this to supplementary. All right, strategy for proof. The final reason in the proof, general rule. The last reason explains why the last statement must be true. Never write the word proof for any reason in a proof. The illustration, the final reason in the proof of theorem 1.7.6 is the definition of supplementary angles. If the sum of measures of two angles is 180 degrees, the angles are supplementary. Okay. All right. Study the formal proof of theorem 1.7.6. The exterior sides of two adjacent angles form a straight line, then those angles are supplementary. So yeah, there's the extension to supplementary. If the exterior sides of two adjacent angles form a straight line, then the angles are supplementary. So there's the exterior sides of two adjacent angles. That would be, looks like that's supposed to be an E. So EF to FG. That's a straight line, right? So a straight angle. And those are the exterior sides of the adjacent angles 3 and 4. Well, those are going to sum to 180. I mean, it's really, from a non-math, technical math proof standpoint, it's really trivial. So, like, we know, I mean, I'll do a engineering proof right now. Okay, this is a straight angle. Okay, that's 100, which we know measures 180 degrees by definition. Okay, now we've got adjacent angles where we know that when you have adjacent angles, they don't overlap, that you can kind of sum them to get a total angle. So we can just see that the angle, our intuition, based on what we've studied in geometry, our engineering intuition, just looking at this, tells us that the measure of this angle EFG, the 180 degrees, is going to be equal to the measure of angle 4 plus the measure of angle 3. Well, since these two angles sum to 180, that means they're supplementary. So there you go. There's the engineering proof. It's kind of like you're using your intuition based on what you've already learned, the theorems you've learned in math. Okay, so you can see how they say it more, what I just said more officially here. Angles 3 and angle 4, and the line EG, measure of angle 3 plus measure of angle 4 is equal to the measure of angle EFG. That's the angle addition postulate. So that's what I needed to state, but I didn't remember from a non-mathematician standpoint. Angle EFG is a straight angle, so measure of angle EFG is 180 degrees. So measure of angle 3 plus measure of angle 4 is 180 degrees. So that means they're supplementary. There you go. But then they stated they put substitution here, right? That's technically how they equated, how they substituted this into the angle addition postulate formula. The final two theorems in this section are stated for convenience, we suggest that the student make drawings to illustrate Theorem 1.7.7 and Theorem 1.7.8. All right, if two line segments are congruent, then their midpoints separate these segments into 4 congruent segments. Yeah, of course. If you have any line segments that are congruent, that means their measures are equal. Then when you cut those lines in half with the midpoints, then the lines that have been cut in half are also, they're all going to be congruent. If two angles are congruent, then their bisectors separate these angles into 4 congruent angles. I mean, yeah, to me, of course, this is a good example of, from an engineering, non-mathematician standpoint, our intuition tells us that this is true. But our intuition is, our non-mathematician intuition is only based on the what has been rigorously proved by mathematicians, but that's okay. That's what mathematicians do. They make it to where non-mathematicians don't have to rigorously prove anything. They can just use what the intuition they've developed from studying math to kind of informally state truths or assume truths. Okay, so we're not going to work any example problems from this section. We'll go ahead and move on to Chapter 2.